Okay, so today we are going to transition from neurophysiology to modeling that physiology with a computer or mathematically. So in the last lecture, we briefly saw what neurons look like, what the neuronal membrane looks like, and currents passing through it. Now, I also mentioned how this cell, how all cells maintain a voltage difference between their outside and inside, and difference of concentrations between ions, right? So here, this is a recap of the same thing. So you can see that inside the cell, you have more potassium ions, the blue one, rather turquoise ones, and fewer sodium ions, right? And fewer chloride ions compared to the outside. Within the cell membrane or within any closed container, it's very hard to have difference in charges, in number of total charges. You have to balance the positive with the negative, right? If you can count that with just a few charges in terms of moles and so on, you will very quickly get a very large potential difference. So inside of the cell also has anions which are pretty large, which cannot move through the cell membrane. But these cations and chloride ion, they are single atoms, so they can move through various kinds of ion channels. Anions are usually, if they are biomolecules, then they are very large and they cannot move through without active transport or some other mechanism. And actually, these ions also move through active transport. And this concentration difference is maintained by various kinds of ion pumps, which use energy to push sodium ions outside and potassium ions inside, chloride ions outside. Some are actually connected to other ATP-driven pumps, and they passively move ions along with the sodium and potassium. So there is a whole set of machineries on the cell membrane which control this kind of ion balance. And in your resting state, you have two kinds of forces acting. One is chemical gradient. So you have potassium concentration high inside and low outside. So by laws of diffusion, potassium will tend to move out, right? And that actually puts a kind of force on the membrane for currents to move or the ions to move. On the other hand, the inside is negative and the outside is positive. So there is an electrical gradient. So there is an electrical force which is trying to move the charges, positive charges inside. When these two things are balanced, there is no net movement of charges. And that is called equilibrium. And for each ion, if you look at one ion in isolation, you will see that it has a specific equilibrium potential. So naturally, for example, potassium has higher concentration inside. So whatever the cell's resting state is, there will be certain concentration of potassium. So if you took away the voltage difference, then what will happen? Potassium will move out under diffusive pressure. You need to apply some voltage in order to keep it from moving out. So that is your equilibrium for potassium. If you get rid of all other ions, you are not contributing anything else. And that equilibrium potential is called Nernst potential. And Nernst actually derived it from basic rules of physics, basic laws of physics. And this is the expression. So for each ion species, depending on the concentration inside and outside, you will have an equilibrium potential for that ion. And remember, this is for the ion species, not the specific channels. You may have 10 different potassium channels, but the potassium equilibrium potential is the same for all of the channels for a given membrane, given cell or given part of the cell. Okay? And here R is your universal gas constant, T is absolute temperature, Z is the charge of the ion or valence of the ion, F is Faraday's constant, and C out is concentration outside, C in is concentration inside. Any questions? So for individual ions, this equation gives us what will be the equilibrium potential for that ion. And we have seen this before. We can think of the cell membrane as lipid bilayer with channels embedded in that. Those channels allow current to pass, so they act as resistor or conductors, and the lipid bilayer acts as a capacitor because it is an insulator, right? So insulator dividing charges or dividing voltages is a capacitor. And you can draw the equivalent circuit of this like this. So for this also, so when we are saying some general resistance, this Rm, it is called membrane resistance. It is actually the combination of all ion channels which allow ions to pass in the resting state. Okay? So this is just clubbing all of them together as a blanket. And this resistance is an ohmic resistance. What is an ohmic resistance? Yes. So the resistance is constant, independent of voltage or time or anything else, V and I. And the equilibrium potential that we need to apply in order for any currents to prevent any ions to move through the membrane, that is the resting membrane potential, or in the case of steady state, this is the resting membrane potential. But not all neurons have a resting membrane potential. Not all neurons rest. Some neurons are naturally spontaneously spiking all the time. So this is a concept which applies to some cases. Physiologists usually idealize situations like this, but the reality is quite different. Whenever you go to an actual experiments, things will be very different from what you see in textbook or paper. So here the convention is a little different. So the ER is looking this way. Out is outside and in is inside of the cell membrane. And your equilibrium potential is shown in this direction. And you can also have different directions based on what the tendency of charges to move. So here, this is the passive membrane. We are not talking about any of the ion channels which change with voltage or time. Okay? And ohmic resistance is called passive resistance. So when we say passive versus active, you may remember from high school, your resistor, capacitor, and inductor. These three components were passive components. Okay, whatever circuits you made with this, these are passive circuits. But when you introduce transistors or valves, then it becomes active. Okay? And in that case, the current is not linearly dependent on the voltage. That means you cannot, if you plot the voltage with current, or the current against voltage rather, this is called IV curve. This slope will be your resistance. Okay? But in case of active component, you won't have this kind of straight line when you plot the current voltage relationship. You may have something like this. So the membrane resistance is in general considered passive. So that is baseline resistance that you have. And on top of that, we'll have the sodium and potassium conductances and other ionic conductances which change with voltage and do not follow the straight line kind of curve. Now, forget about the ion channels as separate entities, but think of the cell membrane to be just resistance and capacitance in parallel. This is called a parallel RC circuit, and it has the equilibrium resistance or equilibrium potential as part of the resistor branch. Now, this is one small patch of membrane, and when you think of a neuron, you can think of this as many small segments. Okay? And here, this is indicating the outside of the cell membrane, and this is the inside. The resistance, when you have some current injected here, what happens to this? Part of the current will flow through the cytoplasm. Cytoplasm has lots of salt. It is more like seawater because everything, the life form evolved in sea, oceans. So it is a conductor. But even a conductor, unless it is a superconductor, it has some finite resistance. Okay? So this is called axial resistance, cytoplasmic resistance, internal resistance. There are multiple names for this. We'll use axial resistance. And the current that passes through will be axial current. And part of that current will actually leak through this resistance, RL. This is the membrane resistance. And also part of it will go through CM if the current is changing. If the voltage is changing, then capacitor allow currents to pass through. And the outside part, we are showing it as the resistance of the outside, RO. But normally when you are doing an experiment, you will have selene all over this, and you will be putting your ground electrode here. So you can ignore this part. This will be so small compared to the other resistances that you can consider this to be all short circuit. And that kind of makes our life easier. Okay. So this is the basic idea of how a neurite, long cylinder-like neurite looks like. And actually you have seen the figures in the last class. All neurons have cylinder-like or thread-like structure, axons and dendrites. And those can be thought of ideally as a cylinder, which is allowing some current to pass through the membrane and rest of the current to go along the axis to cytoplasm. Now we can look at this in an ideal scenario. Assume that you have a constant diameter cylinder. The membrane is also uniform, so its properties are not changing with length, and that is this bit. Now, if you think of the currents that are going through these, then there is the axial current, I, and think of unit length. Okay. Now we are talking about these small letters. We are talking about quantities per unit length. We can think of axial resistance of unit length. Similarly, membrane resistance of unit length and capacitance of unit length. Okay. We are not considering the cross section right now. Now, in that, you will have voltage difference between two parts of a small compartment, right? And if your current IA is going along this, what is your rate of change of voltage with distance? So if this is a small length of delta x, you can think of the change in voltage to be delta V. Okay. So what is the rate of change of voltage from here to here with distance? That is partial derivative of V with respect to x. So everybody knows a little bit of calculus, what derivatives are. And we are putting delta instead of dv by dx because we have two parameters. One is distance, another can be time. Now, if you think of what the voltage difference would be, delta V, it will be IA into RA. Okay. Now, and then if it is distance is x and RA is per unit length resistance, then your total resistance is RA times delta x. Then you have this voltage drop. So you can say delta V equals IA RA delta x, or delta V by delta x is IA times RA. And when you take this to the limit, x is becoming smaller and smaller, close to 0. then this becomes a derivative by definition. Okay. Actually, I made a mistake here in sign. Can anybody tell what is wrong? Exactly. In derivatives, when you are increasing, the derivative is positive. If you are decreasing, then it is negative. But if your current is going from V1 to V2, then V2 is lower than V1, so it should be a negative sign. But don't worry about these signs and so on. These matter when you are trying to implement it, either by hand or by computer. But just remember the concept, what is going on here. Okay? So current is flowing along the cytoplasm, and because the cytoplasm has a resistance, there is going to be some voltage drop. And that voltage drop, the distance is proportional to the axial current times the axial resistivity. Now that is one part, that is the drop. Now, why is this drop happening? Because if current is lost, that current must go somewhere, because conservation of charge cannot be created or destroyed. So the total amount of positive charge and negative charge will end up being zero in the universe. So that current just cannot vanish. It has to go somewhere, because these are ions or electrons or whatever. They have to move somewhere. And that is the membrane current that is leaking out through the resistance here and the capacitance here. So whatever you are losing here is actually going here. So if you have difference in currents, then whatever that is, I will see this side. So the drop in your axial current is, if Im is the current to the cell membrane per unit length, then for delta x length, it is multiplied. So total of Im times delta x, that is your change in Ia. Okay. Here also you can put a negative sign if you consider current moving out as negative. And then again delta Ia by delta x is your Im. Correct? So far so good. Now we have already one derivation there. Right? So we can say okay, I am just calculating second derivative of that side, and that gives me this partial derivative of Ia with respect to x, first order derivative. And I have already calculated that Ia by delta x is negative of Ia. Okay, so far so good. Or we can say correct. Now we can split up that Im bit into its components. So if you refer to this circuit, Im has two components. One is going through the resistance, another is going through the capacitance, right? So the part that is going through resistance will be maybe I have a slide for that. Okay. No. Okay, let's stay here. L equals V by R. So V minus L, because the resistance also has a small reversal potential associated with it. And that is represented as the battery in this circuit. Here, that EM. So I can call it EM. Okay. So if this is V, the total voltage across this is V minus M. Then there is another component which is going through the capacitor. And everybody remembers this equation for capacitor, right? This was in your 11th or 12th. Q equals CV, the total charge across a capacitor is its capacitance times the voltage. Actually, the definition of capacitance comes from this, like the total charge is proportional to the voltage, and then you use a proportionality constant called C, and then you have this equation, and C is defined as the capacitance of the capacitor. Now, what is current? Yes. So rate of charge movement. So you can say if you take derivative of both sides, capacitance is constant and the voltage is changing with time. So this is a partial derivative with respect to time. So your overall equation becomes this. Okay. Now you can put it here for Im, and you have the equation for a KV. Okay. So I'll just replace Im here. Okay. Or if we rearrange, okay, this equation is expressed in many different ways, but we'll go for one specific way of defining this or describing this equation. Now you have this two-part equation. Okay. One side is how the voltage changes with distance, and another side is how it is changing with time. They are getting related. Now you can also do something. This should be small cm. Okay. You can multiply both sides by Rn, and what you have is Rm by Ra times partial derivative of V with respect to distance. Then moving this forward, okay, and we can simplify these two components by calling this one lambda and calling this thing tau. Okay, if you look at this actually has unit of length, and this has unit of time. R and C, resistance and capacitance, when multiplied, it gives time. Yeah. No, because axial resistance and membrane resistance per unit length have different units. Okay. Now a bit about converting these things into absolute values. Okay. Think of a small cylindrical section. This is radius A and this is length X. That is what we have been considering, right? And we are saying that per unit axial resistance is RA. Okay. So if the total resistance of this block is capital RA, then what will be the per unit value? Resistance is inversely proportional to cross section. So you will have to divide by pi square, and then you have to multiply by length. Okay. So if you call this L instead, you have length square below and length on top. So this is ohm per centimeter, right? On the other hand, if you think of the membrane resistance, Rm, so this is per unit length. What is the total surface area of the cylinder? 2 pi r square. Surface of the cylinder. 2 pi? Exactly. 2 pi a delta x, or yeah. So if Rm is the total membrane resistance, in this case, as we increase the surface area, again, it divides, and for unit length, you will have as you increase the length, it will be proportional to the length. Sorry, my bad. Okay, total surface area for unit length, it will be 2 pi a. Will be the surface area. So total resistance okay, somebody help me. Here conductance will be no, not this RA, but RM. We are talking about RM now. Small RM. Yes. Okay, so GM divided by total area, right? No, I was saying RM 1 by GM, right? Yes. Right. So for actual GM is per unit length. It's per length, right? So if you just do the dimensional analysis here, so using that you can actually cut out all the length, and you get eventually you end up with length at the end when you do RM by RA. All lengths will go away? Not all lengths. It's RM. RM is actually it's value area, right? Yes, RM decreases with area. Yeah. So right? You have an L square and you have an L. So L and L cut off, so you have 1 and on the top. So 1 unit of length on the numerator, so you end up with a unit of length. Okay, think of it this way. So if you have 1 unit length, okay, you have a 2 pi a times. Okay, we have another thing called R capital N. This is specific membrane resistance. So this is for a unit area. Okay. So you have 2 pi a as the area. This should be your small rm, right, for unit length. And as you increase, these are just parallel resistances getting added together. Okay. And therefore, as you increase the length, now your resistance should decrease. Okay. Yeah. R is the axial. Yeah.
It depends on the area of the cylinder.
Yes.
While RM depends on the surface area.
Yes.
So, while for RM, we took a units area,
Mm-hmm.
and then we are multiplying with delta x or what we are with x.
Yeah.
So for RM, we are taking the unit surface area, and then we are multiplying it with delta x or x. RM by it would be like 2 pi a.
Okay, actually, the mistake I made was this RM we are talking about as unit length resistance, right? So it should not be bothered with the area, because the area is already, this surface area is already included, right? So it should actually just keep decreasing, isn't it? As you increase the length, the surface area is increasing proportional to delta x. And as you increase the area, the resistance will be going down, so that delta x comes below. Okay. Does that make sense? Yes, unit length. We are not, when we are talking about Rn, we are not talking about the, we have already included the perimeter of the cylinder. Okay. So unit length cylinders resistance is Rn, small rn. Okay. Now if we increase the length, then what happens? The surface area increases proportional to the length, so the resistance should decrease, right? So Rm is R small m by length. Okay. Now this is ohm. This is also ohm. These are absolute values. Okay. Then this will have ohm centimeter or resistance times length. L into Rm. So length multiplied by resistance, it will be ohm centimeter. Similarly, R small a will have ohm per centimeter. And you can also talk about when you don't have unit surface area, you can include the surface area, and in that case, you will have specific resistance, specific membrane resistance, which is indicated by R capital M, and similarly, specific axial resistance, R capital A. Similarly, C capital M for unit areas capacitance, and C small m is unit lengths capacitance. Okay. Yeah. Yes.
Which direction of taking
Delta x is always to the right. Yeah.
That's the confusion because I am moving like this,
Mhm.
but delta x is in this direction.
Yeah.
So delta x times I am.
But is current a vector? Are you doing vector calculations here? Yes, everything is, we are considering only one unit length here. So here the IA, delta IA is over total. Over delta x distance, you have delta IA drop of axial current, right? And IM is membrane current per unit length. So for delta x, the total membrane current will be Im times delta x. Yes. Mhm. Okay, so the results of all the derivation are in this slide. And this equation was actually developed long before neuroscience developed this way in the mid 1800s. So everybody heard of Lord Kelvin, the temperature, absolute temperature unit is named after him. So his actual name was William Thomson, and his lab was on the banks of a river called Kelvin. Okay? And he was such a great scientist that Queen Victoria, he was a like plebeian, ordinary person, and he was given the baronhood. So that is what gives you the lord title. So Victoria made him. Usually barons are of a specific place. Okay, like Lord Bentinck. So they will be the Baron of Bentinck. Similarly, Victoria gave him the baronship of the river. That's why he is called Lord Bentinck. Okay, and what he did was in the mid 1800s, telephone was just invented, and they were trying to connect the Americas with Europe. And the process for that was, because telephone was wired at that time, they just lay very thick wires through the Atlantic. Okay? So there will be ship with big coils of telephone cables, and they will be dropping the cables in the ocean as they travel through the ocean. Okay? And other ship will at one point will run out of the cable, and another ship will come with supply, and they will tie the cables and keep going. Now this, like thousands of kilometers of distance, it is very different from the wiring in your house. Even your house has copper wire, which is a very good conductor, but even that has a finite resistance. And no matter how good a conductor you use, when you get to that kind of length, you are losing electricity. You have a lot of resistance, but also when you can try to still push current through by increasing the voltage, right? But as you increase the voltage, no matter how well insulated your cables are, some current is going to leak through. Okay? So that is why he actually came up with this equation to figure out how much voltage and current you need in order to pass signal through these telephone cables. And that is why this is called cable equation. Okay? This is also called core conductor equation because in the cell neurite, the cytoplasm is at the core, and in cables also the core will be metal, and then there will be insulation on outside. So this is also called core conductor theory or cable theory. Okay? And with this, by solving this equation, you can actually calculate how the voltage will drop with distance or with time. So for simplification, what you can do is we have already done this bit, right? Rm by Ra lambda. Sorry, this is not lambda, this is lambda square. So we can also get rid of the En and consider the voltage to be measured with respect to resting membrane potential. Now, if we measure distance in terms of lambda, we take lambda as our unit, then we have a new variable, okay? And we can measure time in terms of tau. So we have a new time unit, which is tau. Okay. If we make this change of variable, then these parts will vanish. They cancel out. And what you have is del 2v by del x2 equals del v by del capital T plus v. Okay, this is a much simpler equation and it helps the solution. Like you can solve this also, you can solve this also. But this has an important meaning. This lambda is called space constant. If you solve it, for example, for an infinite cable, okay, assume that your cable has infinite length. Okay, so you don't have to worry about what is going to happen at this end. And you hold this at a fixed voltage. How will you see the voltage here? If you put something to measure the voltage, what will be the voltage here? Okay. So if it is steady state, then change with time is 0. Then it becomes del 2v by del x2 equals v. And this equation is easy to solve. Okay. And your answer would be okay. So basically, the voltage will drop exponentially as you go further and further. And this gives you a good intuition about what happens in a neuron under some conditions. Based on lambda, you can imagine that neuron may be many lambdas long or few lambdas long, because you are converting the distance length into this lambda unit. So that will tell you, if you are lambda distance away from the soma, if you are holding the soma at a particular voltage V0, then you will have 1 by E times V0 at lambda distance, where E is the base of natural logarithm. Okay. So this gives you an idea, any kind of voltage, how far it will have influence. So if a neuron has a very small lambda, that means the voltage is going to drop very quickly. And as you go from one point to another, you will have very little effect of that voltage. Whereas if you have very long lambda, that means very long distances in the neuron will still be affected by voltage changes in another point. Okay. So when a neuron has a large lambda, we call it a compact neuron, electrically compact, because it's like everything is very short distance. So when you make any electrical change, even long distance appears like short distance. And tau tells you how things change with time. Tau is called time constant. And again, if you keep the space constant, if things don't change with x, then you have this equation. And then it is just solving the parallel RC circuit. E to the power minus some constant times e to the power minus t by tau. Okay. That is how your voltage will drop over time. If you give a small current injection, your voltage is going to change with time. And similarly for charging. So these two have important consequences. Now think physiologically. You have a neurite or a neuronal arbor. Okay, in the simple case, you have a neurite like this, and you have, say, synaptic inputs coming at different locations. This is your soma. So if they arrive simultaneously or at different times, say, independently, then the lambda tells you how influential this will be on the soma. How much of this signal will arrive here? You have some deflection, EPSP, say 5 millivolt, and lambda tells you how much it will attenuate when arriving here. It can become 1 millivolt. depending on lambda. Okay. And you know that this will be a smaller attenuation. So if you had 5 millivolt EPSP here, it will have probably 2 millivolt here. So this tells you how a neuron can integrate signal in space. Integrate means putting together. On the other hand, what the time constant tells you, if the time constant is large, then the decay will be slow. So any signal, if you have incoming signal like this, then over time, it will flatten out like this. Or if you give us a direct current pulse, let's not go into EPSP. So for the same current pulse, if your time constant is low, it will be like this. If your time constant is, if your time constant is long, then this will be long. If your time constant is short, then this will be short. So this affects how over time the signal gets spread out. And this tells you how the temporal integration will be. So if the signal is spread out, then if another signal comes a little later, so first input came here, then another input comes here, then by superposition principle, these two will get integrated, come together, and you'll have something like this. If the time constant was very small, then what would happen? You had something like this, then you had something like this, and your result will be like this. So here it could integrate the two inputs to get a larger total amplitude. Here it could not, because the time constant was small. Okay, so this is one of the fundamental principles of how neurons can compute things. So this is how they put together their inputs. Yeah.
The greater the space constant, the larger will be the magnitude of EPSP reaching the server.
Yes.
But that's kind of opposite to what that is. The last one, A into the minus lambda. The greater the lambda, the more fast the decay will be, right?
The greater the lambda, the more fast the decay will be. Yeah, as you go further.
It's X by lambda, it makes sense.
Let me see, did I make a mistake? Yes, it should be x by lambda because we made lambda our unit of length. Yeah, sorry. Okay, and the distance measured in units of lambda is called electrotonic length or electrotonic distance. So sometimes people talk about the electrotonic length of a neuron. That is what is the total distance in terms of lambda units. Okay, now we saw these equations, but these equations can only be solved analytically for the simplest of cases. So when you assume that either time is things are not changing with time, or we assume that things are not changing with space and so on. So only the simple cases are what we can measure. We also made a big assumption that the neurite is uniform. So Rm and Ra are constant everywhere. As soon as you start changing those over distance, then you are in a big mess. Or time. If in any way those change, then calculation becomes impossible by hand. And there are no analytical solutions. So all the physicists here know that when you have second order differential equations like this, as your coefficients become functions of your independent variables, it becomes very hard or impossible to solve analytically. So neurons in reality are nothing like uniform ideal examples of physics, right? Everybody knows the spherical cow joke. Yeah. Some people don't know. No. So after the atom bomb, the project for atom bomb was in the Los Alamos laboratory. Okay, that was called Manhattan Project, and US had gathered together probably the largest crowd of great physicists at Los Alamos to build the atom bomb, including Richard Feynman. Albert Einstein did not go, but Robert Oppenheimer, John von Neumann, everybody was there. All the big shots in physics and mathematics you can think of, they were in that project. And of course, atom bomb was a big success. And all these scientists, geniuses were very publicized. So everybody used to go to physicists for solution for every problem at that time. Now like they go to computer scientists or AI guys. At that time, physics was the hot cake. So some farmer in Minnesota found that his cows are not producing enough milk. So he wrote to the physicists that, okay, I have a problem. My cows have stopped producing milk. What can I do? So the physicist starts, let's assume a spherical cow. Okay. So far we have done the spherical cow. Reality is nothing like this. And that is where this gentleman comes in, Wilfried Roll. He was a fantastic guy, just passed away in 2018. And what he did, he was a physicist, but he did his postdoc with a neuroscientist, a Nobel laureate called John Eccles. Although they did not get along very well, his career was hampered by that. But what he actually, the reason for that conflict was his theories were conflicting with Eccles' ideas. And now we know that although Eccles won the Nobel Prize for his work, that was good work, of course, but the theories that he proposed were wrong. Kroll was right. Okay. So what Eccles' idea was that these dendritic structures and so on do not matter. Everything happens in the soma and through spikes. Okay. And what Roll was complaining about was that, okay, just from basic physics, I know that as the signal propagates along the dendrites, it should get attenuated. And he went through a lot of analysis and simulations in order to show that. And now we know that, yes, dendrites do that kind of computation. And he was right. So initially he did all these basic ideas. He also solved it for simple kind of structures. So if you think of a tree structure of dendrites, where they are just symmetrically branched, for that case, he derived some analytical solutions on the relationship between the diameters of each of the branch neurons to their parent and how that can be resolved into the cable equation, like a straight cable. That is called Rawls' law. You don't need to learn this because we don't use it anymore. We don't need to use it anymore because we have simulators. So next what he showed was that you could take a neuron, like a branch structure like this, and this branch structure is practically impossible to solve by hand because there are too many terms. And you consider a small patch of membrane like the RC circuit. And then you connect those up with axial resistance because these cylinders are connected by axial resistance. So you have an equivalent circuit of this neural arbor. Okay. And then you can calculate for each of those what will be the current and voltage and in which direction they flow. And then you can calculate what it will be at each point. And here you can also change the resistance, capacitance, and axial resistance to have to account for variable widths of the dendrite and also variable ion channel concentrations. Okay, how are you doing in terms of time? 12. Okay, I'll have to be quick. Now, so far we saw the passive membrane. Actually, our equation did include all the membrane currents as IM. We can also use this equation for active membrane, but we cannot solve it repeatedly. And for that, we'll have to use Rawls method. So now, how do we handle the ion channels? We know that neuronal membranes are not like simple resistance. They spike, their conductance changes nonlinearly. And to figure out how that happens, how the spike happens, Hodgkin and Huxley did their seminal work in 1952, before 1952, where one of the key techniques they developed was this thing called voltage plan. Okay, their experiment was with and at that time people used to use many different animals and model systems in order to do the best possible experiments. So what they used was squid giant axon. Squid, if you see, say, David Attenborough movies, then you know that squids can run very fast. They swim away. They have something like what do you call it? Jet propulsion kind of system, where they run away very fast, and that is controlled by a giant axon. In the last lecture we talked about how the diameter influences the speed of propagation of action potential. So this particular neuron is responsible for this escape response in squid, and it is very thick. It's almost 1 millimeter in diameter. So they used that as their model system. And what they did was that they want to see the conductances of the current at constant voltage. What they figured is that if you just give a current injection, constant current injection, the axon starts spiking. And during spiking, things are changing so fast, you cannot really measure anything. And too many things are changing simultaneously. So that is difficult. So what did they do? They made a system where they could hold the voltage constant. Okay? Now think of this cylinder as the axon. And in that, they put two wire electrodes. One was for measuring the current and another for another for measuring the voltage, controlling the voltage. Okay. So these op-amps, you can simply think of them as they see two values in their two inputs. And what they try to do is they make their output so that the two inputs become equal. So they try to remove the difference between these two inputs. Okay? That is the basic principle of op-amp, what it does. Now this VC is a common voltage. You want the voltage to go to a particular value. So that is something you can explicitly give. I want the voltage of the squid axon to be 10 millivolt. You feed that here, and here, this is the measured voltage of the axon. So this wire is here, and this is getting connected directly here. So the op-amp will try to send some current output here so that this difference goes down. And that means this will become VC, common voltage. That is what the axon's voltage would be. And then this part is measuring the membrane voltage and also the membrane current. So this is outside of the cell membrane. What they did was actually put the axon inside a cylinder, conducting cylinder. So that is represented by this bit. So any current that is passing through the cell membrane will get captured by this electrode, and it is getting grounded. Okay. And this is what the current injection is going to be in order to maintain the voltage. Because if you keep the voltage constant, you'll have to inject some current to keep it at that level. Okay. Now, the equivalent circuit of this whole system is this. You have the membrane resistance is inverse here. GL is leak conductance. So it is just another way of talking about membrane resistance. We are talking about conductance instead of resistance. You have CM, leak reversal potential, but in addition, you have these ionic conductances. So sodium and potassium ions flow through the membrane. So they will have some conductance, and this conductance is variable. That is what these arrows on the resistance symbol are indicating. And they will also have their Nernst potential, equilibrium potentials for each of these ions. And because sodium has a force moving it towards inside, the sodium battery is inwards, and potassium has the chemical force moving it outside. EK is representing the potassium reversal potential and it is outward. Okay. Now, what we had put as IN earlier is this bit. So this is the current through the resistance or leak resistance, okay, Rn, and all these conductances are getting together in this summation. So for each conductance, you multiply the conductance by the voltage difference from the equilibrium potential, right? So conductance is just the inverse of resistance. It is like V minus Ek divided by Rk. 1 by Rk is Gk. And this way, again, you can calculate the total current that is going through the membrane. And how did Hodgkin and Huxley measure these individual ionic currents? In their time, what they did was they replaced the sodium in the seawater with a chemical called choline. So instead of sodium chloride, you are giving choline chloride. So you have very low sodium in the system, and you do a voltage climb experiment there and measure the current that is passing through. And at that low sodium, you know that the sodium current is going to be 0 because sodium is not flowing through the membrane. And then you also measure the current with potassium and sodium both present, 100% sodium, full sodium. And then if you subtract this no sodium current from sodium potassium current, you know that the potassium is constant. Potassium current is constant between these two scenarios. That is an assumption that sodium and potassium currents are independent of each other. So if you then subtract the low sodium current, that is the potassium current, then you have the sodium current. And what we do today? Today we have figured out a lot of toxins which selectively block these specific ion channels. Okay. In their case, it was all sodium. But now we know that each of these ion channels have many variations. So what they actually found was this K is called KDR, delayed rectifier potassium current. Okay. And there are like lots of variations of potassium currents which have different properties, and they can be separated by specific toxins. These are called antagonists. So those chemicals go and attach to the channel and block them. Okay. But that is the basic idea. In their time, they did it very cleverly. And they took this voltage clamp, did this voltage, repeated the voltage clamp at different voltages to find out the steady state value of this conductance. Okay. And similarly, this is for potassium. And what they figured out was that potassium conductance could be explained as something like a fixed maximum value times a fraction to the power 4. N is a fraction. And what they came up with, again, they did very basic logical reasoning from physics. Okay. They assumed that there are these particles, which we know now are ion channels. There are these particles on the membrane which open and close to let the ions pass through. Okay. So for potassium, this was N particle. And N is also representing the fraction of the particles that are open. Now, this transition between opening and closing of the particles, they modeled that as a first order chemical reaction. So you have N open, then 1 minus N fraction is closed, and you assume that there is a rate, forward rate of going from open to close, backward rate from going from close to open. And then you have that equation for the rate of change, rate of opening. And then if you solve that, you have this kind of equation. Okay. And these are very vital. This N infinity and tau N. N infinity is steady state value, steady state variable, and tau N is the time constant of the gate. So ultimately, we know that these Tn, 4 Ns, are actually 4 parts of the potassium channel. These are 4 gates. And each one has a probability of being open, which is N. Now, the probability of all 4 being open simultaneously is N to the power 4. So these are the plots of N infinity and tau N. So you know that, so this is the steady state value of open probability or open fraction. So you know at minus 75, very small fraction are open, and as you increase the voltage, more and more open, and they become fully open. Okay. And tau n indicates how fast this opening or closing happens. So at low voltages, it is actually quite fast, but at high voltages, it becomes slow. So once it opens, it stays open, but there is no closure here. Yeah. For scaling. So here are alpha and beta from Hodgkin and Huxley's original paper. So again, you can see that alpha is decreasing and beta is increasing with voltage. This is what physiologists use for characterizing ion channels. So for different ion channels, you will have different equations for these gating parameters. So for sodium, unlike potassium, potassium was going up and getting steady. For sodium, it is going up and coming down. So for that, they came up with three gates. Sorry, two types of gates. Three of them are activating and one is inactivating. M is called activating gate and M is activation parameter and H is inactivating gate and inactivation parameter. So again, these are representing the fraction of gates that are open. And we have seen in the last lecture how activation and inactivation can work. Right? And this actually helps to explain why it should go up and then come down. So same equation, same form. So alpha beta for M have the same shape as for N, potassium. So this potassium just activates, doesn't inactivate. But when you look at H, it is the opposite direction. As you increase the voltage, the fraction open is going down. Actually, this is plot of alpha and beta. But yeah, here you have N infinity tau N, H infinity tau H. Okay. So as you increase the voltage, M is increasing, but H is decreasing. Now, if you have M cube H, this is increasing, this is decreasing. At some point, this is dominating. And as you go too far, this will be dominating in this product. Okay? And that explains your rising and falling state of this channel. And actually, if you plot these two H and M together, then you will see something like this. So, and the product is the conductance, actually to the power 3 into H into. Now, in this part only, you will have a high current flowing through, high conductance. So this one is called a window current when you are in that region, because there's a window of variables where things are good. If you are too far here, then N is so small, your conductance is going down. If you're too far here, your H is so small, your conductance is going down. Okay, now I'll just finish with a quick example of how one can simulate this whole Hodgkin-Huxley experiment. There you go. So this is a simulation of Hodgkin-Huxley's experiment with squid giant axon. Okay. So what we are doing here is we are using a simulator called Moose, which we developed in the lab in collaboration with NCBS. And this is a very old demo from 20 years ago, but it's still good because it's a very good tutorial for basic physiology and especially Hodgkin-Huxley models. And it has all the parameters that Hodgkin-Huxley did use. So you can control the concentrations of the ion channels in these fields. Okay? And using that, it calculates what will be the Null's potential for each of these ions. You can change the temperature, and it has an idea about Q10. Everybody knows what Q10s are. Q10 is this rate of change of a chemical reaction as you by 10 degrees. Yeah. So you can compensate for temperatures in this way. And Hodgkin and Huxley actually did their experiments at very low temperature because that is the sea temperature around England, right? So they just used whatever the local conditions were. And when you switch to say mammalian system, you are doing it at much higher temperature. Theirs was something like 16 degrees Celsius, I think. And in humans, you'll have 36 degrees Celsius. Yeah. So that kind of compensation needs to be made. But remember, these ion channels kind of span species. So squids, sodium and potassium channels are slightly different from humans, sodium and potassium channels. You'll have to make adjustments, but they are essentially similar. And all ion channels now are mostly, I should not say all ion channels, majority of ion channels today can be described by similar equations to Hodgkin and Huxley. That same idea applies. You will have maybe one or maybe two. It is the m infinity tau infinity. That is what electrophysiologists measure. And you get that data. And from that, you can reproduce the behavior of the ion channel. So what we are doing here, we made a passive compartment and then added a sodium channel and a potassium channel and adjusted their absolute conductances. And now we are going to do a voltage clamp experiment, okay? This is our runtime, 50 millisecond. Then we are blocking the sodium channel. All right. And I'll enable overlay plots so you can compare the runs. Okay, so this is channel conductance. This is the current. And this is the voltage, okay? There are two parts in this. One is the actual measured ambient potential. Another is what is your common voltage. So the orange one is common voltage. And the blue behind it, you cannot really see except this bit, is the actually measured voltage. Nothing in physics or in real life can switch from one value to another value abruptly. So when you try to change the step voltage, there is going to be some physical delay and some overshoot. So that overshoot is this blue bit sticking out. So now we did a clamp voltage of 50 millivolts. Okay, we can try 40, run again, 30, run again, 20, minus 20, minus 20 gives almost zero conductance, right? Minus 30, nothing much to see. Conductance goes to zero because you remember that N. So as you reduce the voltage, N is going to get smaller and smaller and close to zero. So your conductance is essentially zero. So this is exactly what, oh no. Somebody else logged in probably. Anyway, so this is exactly what Hodgkin-Huxley's plots were, only looking prettier with colors. And similarly, Hodgkin-Huxley did the experiments with sodium channel open and potassium channel blocked. And that amplitude will be a little different, but let's see. Now we are at minus 30. You cannot see anything because it is zero. Made it zero. Nothing there. 10. Something's coming up. 20. 30. 40, 50. There you go. So from these, actually, there are several things one can do. One can measure the time constant, or rather calculate the time constant from how fast it rises and falls. Okay. So as you take a step voltage, then you assume that the system did not have enough time to adjust to that voltage. So it is going to have some delay. And that you can calculate. And Hodgkin and Huxley actually did all this curve fitting. They essentially did curve fitting by calculating these values to fit these experimental plots. And they did all that using hand cranked calculators. So unlike your pocket calculators, at that time calculators were not as much developed. The latest and greatest technology was you had to rotate a wheel, and you'll have to give your inputs, like change some switches, and you'll get the result. Okay, for taking a cube of something, what is the value? Instead of doing arithmetic by hand. Now we can switch from voltage clamp to current clamp. I won't overlay. So in current clamp, we change the current. We are not controlling the voltage, we are only controlling the current. And here we are giving a current pulse of 0.1 microampere. Okay. And that current will be starting at 5 milliseconds, and it will continue for 40 milliseconds, after which it will come back. And we are not giving any second current pulse. Now if we run this, you see action potentials. All right. So this is just a small example of a single component. Now with simulators, what you can do is you can put together such components via axial resistance. And model the propagation of action potential along an axon. You can also model dendritic inputs. And you can change these conductances. So one thing you may have noticed that sodium is essential for going up and coming down. Okay? Just with potassium, you cannot have that, because with potassium it will just open and not close unless you take the voltage back down. So any part of the neuron which doesn't have sodium channels like that, they cannot generate action potential. There is something that calcium channels can generate. They are similar to sodium. Many calcium channels have similar dynamics to sodium channel, but it is not as sharp as the sodium action potential. So those are called calcium spikes. People often see that in recordings from dendrites. So you will have not full action potentials, but something like ETFPs. Okay. So you can change the ion channels which are present in each compartment to replicate a neuron. For example, you can say, okay, my dendrites are non-spiking. Dendrites do not have as much of sodium ion. So you can reduce the sodium conductance in the dendrites and have high potassium conductance, add calcium ions, calcium conductance, and model this. And there are dozens of types of ion channels of each ion. So there are many calcium ion channels, there are many sodium ion channels, there are many potassium ion channels, and calcium and potassium have probably the largest number of varieties in terms of ion channels. So all of those can be modeled using Hodgkin-Huxley type equations. You have either just one, some g, some m to the power x, some h to the power y. Okay, this is the basic ion channel equation. And when you have this m infinity tau m, h infinity tau h, these are derived experimentally. When you have that data, you can model the dynamics of the ion channel and model the dynamics of the neuron. Okay. And usually experimentalists will block all ion channels except one and study that and get this data. And one last little bit, we did not talk at all about synapses and how neurons communicate. So at the phenomenological level, you don't need to worry about all the things that happen in the synapse. we talked about synapses in the last class. But we talked about vesicles and cleft synaptic cleft. Yeah. So although in actual synapses, you have neurotransmitters getting released and then opening receptors that generating EPSP, right? But for the effect on this neuron, you don't really need to know what exact chemical reaction and stuff are happening here. What you can do is you can start from here. So in phenomenological model, you can have two model neurons, like how you have the model that I'm just showing. You can connect them using a synapse where whenever there is a spike, there is a change in conductance here. That conductance change is representing the receptor channels. So you can have synaptic channels which mimic the conductance change of the receptor. And you have equations for those also. So experimentally, you can see, okay, this is my EPSP. If I'm doing a voltage plan, this is the current that is flowing. Okay. So in an experiment, you can put an electrode here and do a voltage plan, and you will see a current like this. When you are doing voltage plan, the voltage is constant and you are measuring current. So you will see a current like this, and from this current, because your voltage is constant, you can tell what the conductance is. Okay. And that conductance follows very simple mathematical equations. One is called alpha function, which is a pretty good approximation if you do not have a very slow rise of the EPSP or the conductance. Okay. This is called an alpha function. So very simple exponential function that you can use. And if you have more elaborate rise and fall of the current or conductance, then you can have a double exponential sinus function. So in that case, it will be slightly different. Okay. And these are very good approximations of what the conductance you find experimentally. So what you have to do experimentally is to either measure this tau or measure this tau 1 and tau 2, depending on how much resolution you want. And then you have these EPSPs basically replicated on the postsynaptic side. Then if you have other conductances there, sodium potassium channels, you can have spikes being generated. And in this way, you can build large networks. Ideally, what people do in computational neuroscience is they model one type of neuron. Okay, I have a pyramidal cell model. Then I make a granule cell model. And then I make up the connection of in hippocampus. So I am talking about hippocampal pyramidal cell and granule cells. So then you can connect them by excitatory and inhibitory neurons, inhibitory synapses, sorry. This is inhibitory synapse. This is excitatory synapse. And although this doesn't happen, at least I am not aware of this happening in hippocampus, in other brain regions, you can have pyramidal to pyramidal connection. So you build up this kind of circuit. Each of these can be very detailed with those compartments. So you make one prototype, you make multiple copies of that, you make one prototype, make multiple copies of that, and then based on some rule or experimental data, you connect them up. And then you try to model how this system will behave. So you can stimulate your current injection, you can you're doing field recording, if you're injecting field current, then you can model that in terms of some kind of voltage deflection in the cells and so on. And you can also, there are also tricks for measuring stuff like EEG signal. So if you have idea about how current is flowing along the dendrites, then if you have many pyramidal neurons lined up in parallel, then you can calculate what will be the electric field at a particular distance. Again, this is physics. So you can actually calculate the EEG response for a particular pattern of activity in the brain. Okay, that's one aspect of computational neuroscience. There are many other ways of doing this. So any questions? Let me see if I have any other slides. Okay, one last little thing. Okay, one thing to know that these ion channels are, when we are doing this phosphoelectric calculation, we are putting together many thousands of ion channels. So it is a combined effect. Actually, individual ion channels are stochastic. That is why we call M and H as probabilities. Okay, so they can open stochastically, and people do patch clamps for single channel recording, where you can measure the current from a single ion channel. And again, it shows that Hodgkin and Huxley's derivation was correct. They really made a very good guess about the physics of the system. So that's it. Yeah. Both. So especially they cannot overlap each other. They are side by side. And if you're looking at a patch of membrane, there are many ion channels. So each of them are randomly opening and closing with some higher and higher probability as you increase the voltage. Yeah. So you know statistical mechanics, right? So this is just statistical mechanics applied to ion channel. No questions? So nobody understood anything? Yeah.
In the Austin model, we are accounting for only one channel or the overall effect of all the channels together.
Overall impact. That's what I am saying. Like it is stochastic, and M and H are fraction of channels that are open or closed. No other questions? All right.